recording this video is to present the group assignment in Engineering Mathematics 2 PKG 443. I am Muhammad bin Muhammad Ali. This is my group, all my group members which are YEONG, Ushazi and Tan Hongyi. This group assignment contain four question, and I am going to share the solution of question 1. Question 1 is about local extrema application. So the question is the rectangular electric benefit of the region 1 on the x plane 1 until 3, and the y plane is negative pi over 4 until pi over 4. So the electric benefit is inserted so that the temperature at the point xy is dxy equal to 4x minus x square cos y. The question asks to find the temperature at the hottest and coldest point on the electric benefit. The first step is we must find the first and second derivative of the function. Okay, this is the first and second derivative of function. Then we need to find the critical point. We need to let tx and ty equal to 0, and then we get x equal to 2 and y is equal to 0. Then we need to find g to determine local minimum, maximum or saddle point. So this is the formula. We need to find determinant of this matrix. Then after sub x and y, x equal to 2 and y equal to 0, we got 8. And then we need to sub also y x equal to 2 and y equal to 0 into tsx, and we got g to 0 is greater than 0 and tsx is lesser than 0. With this condition, the critical point is determined at local maximum. Then we can conclude that this is the hottest point of the rectangular region. And then we got the hottest point is 4 degrees Celsius. Then at the other point, at the boundary of the rectangular electric inner plate, then we just sub it into dxx, dyy, dxy, and then we find the determinant again of the matrix, and the answer is y. The answer is equal to 1. Okay, we got g 1 and negative pi over 4 is greater than 0, and txx 1 and negative pi over 4 is less than 0. So this condition is also located at local maximum. After doing it at 3 other points, you will get same classification. Then we just put the point into the function to get the coldest part of the rectangular region, and then the coldest part is 2.12 degrees Celsius. So the answer is the hottest point is 4 degrees Celsius and the coldest point is 2.12 degrees Celsius. Okay.
Very good morning to everyone. So for this assignment, I was assigned to present the question for this assignment. So first of all, we need to find the center of the solid. From the questions, the centroids of the solid can be determined by using the given formula below. Here, and a solid G is bounded above by the sphere with a radius of 4 and below by the cone. It's a cone with equations of z equal to square root x squared plus y squared. So based on the formula, we can find centroid. So first we need to find the value of a solid, which is the coefficients of the sphere and the cone. And for this solution, we are using the spherical coordinate to solve it. So after we determine change functions into spherical form, which is from zk into pi square sine angle. So from there, first we integrate rho, so we get rho cube over 3 sine drop. Okay, then we insert the value or limit of the rho to 0 to 4, then we get 64k over 3. Then we continue with the integrations, and at the end we get the value of 12.497 pi k for the volume. So next we can find the moments of mass or the moments of volume for the solids, which is x respect to yz plane. And the formula, the equation is equal to triple integral x zk dv x zk dv, then we change it into spherical form, then we get like this. And from this form, sine squared plus, we change it into 1 over 2 minus 1 over 2 cos 2 plus, which is we get it from the identities of trigonometric functions. So after that, we can integrate the equation just like this. Integrate pi, and after that we integrate angle, sub in the value of angle, then we integrate theta, then at the end the moments of volume for x respect to yz plane is equal to 0. So next we're going to find the moments of volume for y, which is respect to x and z plane. Same, we're going to repeat the same step to the previous slide, which is we're going to change the rectangular coordinates into spherical coordinates. So at the end we get triple integral of rho cube sine squared angle sine theta. And for this sine cube angle, we're going to change it because it is a bit difficult for us to integrate. So we are going to use identities of trigonometric function to change it. So after changing it, then we're going to integrate as usual. And next, for the moments of volume y, at the end we get 0, which is same with the moments of volume s. Okay, so repeat the same step, we can find the moments of volume of z, which is respect to xy plane. So by repeating the same step from rectangular coordinate to spherical coordinates, then we get the rho cube cos angle sine angle. Then from this we are going to use the identities of trigonometry, which is sine 2x equal to 2 sine x cos x, and change it to simplify it. And then we're going to use a normal equation, then sub in the value of limits, then at the end we get z is equal to 2.5606. And then at the end we know the answer, which is the center of the solid G is 002.5606. So that's all from me. Thank you.
Hi, my name is Ho. So I will be presenting question 3. So question 3 will about verify Stokes theorem with the vector field with this equation here, and the region is a rectangular in xy plane. So x, the boundary is x from negative a in a 0 to b. Okay. So we need to describe our solution by sketching the regular region and suitable curve along the region, and explain how this the line integral is equal to the surface integral, and this is the verified Stokes theorem lah. And lastly, we need to give an example from the electrical engineering application which is related to our Stokes theorem. So let's begin. So we need to draw the region first. So it's a rectangular region. For the x coordinate will be negative a to a, and your y coordinate from 0 to b, then it become a rectangular. So we verify for our curve f and normal vector ds first. So your curve f, you're doing product rule, cross product. So in the end we'll get 0, and our n normal vector is xy plane, so you become k lah. 1 is always 1 1k. So we just multiply the dot product of this equation here and the 1k, and we get 0, and our limit will be from a to a, 0 to b, but due to 0 it becomes 0. Okay, so left hand side for the line or the boundary curve, we call it boundary curve. So these are equation here. Okay, the first term, the I will become dx, and your second term 2xy will times with dy lah. You do dy integration. Okay, so we do our C1. C1 is from point A to B. There is no change in coordinate C. It's given as A, but there's change in coordinate Y is 0 to B. Thus your dx will become 0. Your x you need to substitute with A lah. So using the equation just now we use I show. So your dx will become 0. So this term here will become performed lah. Then you're left with your 2xy dy. Then you do your normal substitution for your x equal to a. Then you do normal integration, and then you get negative 2b squared. Okay, so along to C2. C2 is from point B to C. Okay, your coordinate for y is remain unchanged because it's still B, but your x coordinate is from negative a to from a to negative a. So your limit will be from a to negative a, and your this term will be performed due to dy is 0, and you need to substitute your y equal to b. How to substitute that? You get this equation, then you do no integration, then you get this answer here for C2. And for C3 you do from point C to D, which is you can see again for the coordinate x will be remain unchanged, thus your change dx will become 0 because there's no change at all. Okay, but there's a change for your y is from b to 0. So the limit is b to 0. So again this equation becomes 0. So we just left with this equation here, and you substitute equation x equal to negative a. So we can do negative become positive. Then you do your normal integration, you get negative a b squared. And along C4 is the last curve or last straight line, so there is no change in your coordinate y. So your coordinate x will change from negative a to a. So your limit is negative a to a. As usual, your dy is 0, so you do negative 2xy becomes 0, and your y for here is 0, so you substitute with 0 here, so it become gone, left with x squared. So substitute with it, and you get this answer 2a cubed over 3. So in the end, to calculate the whole region here, the boundary region, integral region, so we total up all the value, negative ab squared, negative a cubed, and plus 2ab squared, negative ab squared, plus 2a cubed over 3. So you cancel out this one with this one, and you get this plus become negative 2, and then you cancel out this one. Then in the end, you get 0. So we can verify the boundary region is equal to the surface integral. So using this proof, you will get the same answer 0. So lastly, so how is the application for the Stokes theorem in electrical engineering? Normally this theorem is used to transform a problem expressed in terms of integration over surface into an integration over a closed path or answer. So usually we use to in the region area study is related to magnetic field. So one of the example is that to derive the reducted vector potential of two antennas for the radiation of electric and magnetic field. And that's all for me. And our last question will be presented by our friend Mr. Tan. Thank you.
Hi, my name is Tan. Then I'm going to proceed with question 4. So basically, question 4 we need to choose one topic from week 1 to week 14 and explain about the application in electrical engineering. So the topic had be chosen is divergence theorem. So first, divergence theorem is known as cross divergence theorem. It actually compares surface integral to volume integral. It also relates to flux and vector field through a closed surface, used to find total outward flux for a closed surface. The definition of divergence theorem is the outward flux and vector field through a closed surface is equal to the triple integral of the divergence of the vector field. So according to this equation, the left side of the equation is double integral of surfaces and the right side of the equation is triple integral of the volume. So if we're using the left side of the equation, we need to find all 6 surfaces. But according to divergence theorem, we just need to find the divergence of the vector field and we can solve the triple integral. Question: find the total outward flux of the solid given the vector field F equals to 3xi plus 2yj plus z squared k. So this will be the object. So the total outward flux is the triple integral of the divergence of the vector field. So step 1, find the limit of xyz. So according to the object, we can simply know that the limit of xyz is just 0 to 1. Step 2, find the divergence of the vector field. So the divergence of the vector field is just del operator dot product with the vector field. So we can find that the divergence of the vector field is 5 plus 2z. From previous solution, the divergence of the vector field is 5 plus 2z. So we solve the value to the equation. And we set the limit 1 to 0 to the equation. So after solve the triple integral, we know that the total outward flux is 6. So thank you for listening to our presentation.